So our next speaker will be Professor Olga Veksler from Western Ontario, University of Canada. Is that correct?
University of Western Ontario, yes.
Yeah. So she is a long-time participant of the program, so she has been here for quite some time, and she has been very actively involved with a number of people here. And today she will talk about convexity and other shape priors. Yeah, please.
Thank you for inviting me. I'm going to talk today about different shape priors we have developed in our lab, and this is joint work with Yuri Boykov here in the audience, Lena Karelik, Jean-Ken Liu, and Claudia Neuenhaus. Close enough, I hope. So I'm going to talk about various different approaches we have developed. First, I'm going to talk about segmenting a single object of convex shape, and this is a difficult optimization problem. I'm going to motivate why it's an interesting shape prior. I'm going to develop a discrete energy for its optimization, and then I'm going to talk about how we optimize it. Next, we were interested in question on what can you do if you have more than one convex object, if you have several convex objects you're interested in, and optimization of several objects presents its own challenges. It's not a straightforward, one would think it's a straightforward extension of one object, but there are difficulties there that I'm going to talk about. And again, I'm going to talk about our approach to multiple object segmentation, and then we also got interested in what happens if you have a simple shape prior. When I say simple shape prior, it's a prior which, if you had one object, you could optimize exactly. The energy is not NP hard as opposed to convexity. So if you have, there are several known simple shape priors that you can optimize exactly for a single object, but if you have more than one object with such simple shape prior, there are certain caveats in optimization, there are certain difficulties that come up. And so I'm going to talk about these difficulties and our approach to solving them, which will lead to a new optimization algorithm we call double expansion. So let me start with a shape prior optimization of a single object with a convex shape. And it's not an easy problem. So I'll begin, again, we are working, this whole talk is not in continuous approach, it's in discrete approach. So I'm going to review our discrete optimization framework. And let me start with a simple case when you want to segment one object from the background without any shape priors at all. So suppose we have an image like that, and we want to segment an object, llama in this case, from the background. So we want to get segmentation like that. So in discrete optimization framework, what we're seeking to assign to each pixel a binary variable, 0 or 1. So 0 will mean background, 1 will mean foreground. And we're going to denote binary variables with xp. So xp here is a variable we're assigning to pixel p. And a collection of such binary variables we're going to store in vector x. So x is a collection of binary variables assigned to each pixel. So to address this problem, you typically formulate an energy function which has two terms. First term is here. So it multiplies this binary variable by fp, and fp is unary term which tells whether pixel prefers foreground or it prefers background. So we're going to use positive and negative unary terms in binary formulation. Using positive and negative unary terms is simple, because then we can just have one picture which tells us which pixels like foreground, which pixels don't like foreground. So in this picture here, this shows you all the unary terms. So it's a collection of FPs, one for each pixel. If you see a blue pixel, it means that the unary term is negative. So this pixel prefers, since we're minimizing the energy, this pixel prefers to be labeled foreground, therefore unary term is negative. If you see a red pixel, it means that pixel doesn't, if you see a red FP, it means that pixel doesn't want to be foreground. Penalty is positive. It prefers to be labeled with background 0 because then the penalty disappears. So one picture is enough to illustrate which pixels prefer foreground, which pixels prefer background. And then this another term is used to enforce smoothness on your labeling. So this is the standard paths model. Whenever you have two pixels assigned different labels, like here, you have a discontinuity cost. Here it's written as 1, but of course it can also depend on the contrast between two pixels. If there's a lot of contrast, then penalty is not large. If there's no contrast, penalty is large. So you will get, if you optimize this energy function, you will get, if you set your unary and pairwise terms correctly, you'll get results like that. And as long as, this term, all coefficients are positive, but if you have WPQ coefficients which are positive, you get submodular energy, and you can optimize submodular energy exactly with a single graph cut. So length regularization is very useful, but it has its own biases, very well-known shortcomings. So here we have an input image, and user marked scribbles on this image, blue for foreground and red for background. And here, if you try to find, for this particular example, if you try to find the weight of this regularization term, how much you should penalize the boundaries, it's actually very hard to find an appropriate setting of the weight. For smaller regularization weight, you get very noisy result, and if you increase it very sharply, there's a very sharp for very sort of, I'm not saying it correctly, the difference between this value and this value for regularizer, maybe I have it here, let me actually put it down. So this is what we get for W equals 0.795, and this is what we get for W equals 796. So there is a very little change, but drastic change in the result that you get. And it's not a property of optimization, because we know we're finding global optimum. It's the drawback of regularizer. So it might have, for many examples, it works quite well, but there are examples where for small change in regularizer weight, you're getting drastically different solutions. And therefore, people have looked at other regularizers, not just the length regularizer. There's a lot of work. I'll just mention a few works. So for example, curvature, trying to find labeling where curvature is minimized is a popular approach. Connectivity prior, you might impose on your labeling the prior that object that you get is connected. That's another prior. Star-shaped prior, which I'm going to talk about more later, but it requires an object to have a certain shape. In later portion of the work, I'll describe what it is. Part-shaped prior. Part-shaped prior requires an object to have certain orientation. You divide an object in several parts, and like you can see here, like an airplane, and you require orientation of boundaries between the part and the background to be in certain direction. This talk is about convexity shape prior, and there is some related work or why we're interested in convexity. Convexity happens a lot in nature. Humans are very sensitive to convex objects, and when you perform different visual experiments, convexity often beats other cues, so it's a very strong cue in human visual system. We're very sensitive to it, and there are many objects out there which are approximately convex, especially in medical image segmentation. You have many organs or body parts which are convex, like here in this example, this is approximately convex, and so on. Whereas here it is, also different liver parts which are approximately convex. So it seems like a very interesting and useful prior to work with. And there is some related work in continuous optimization that deals with convex shape prior, but they approach convexity, they model convexity as an n-sided convex polygon. So they're trying to find an object with n sides, polygon with n sides. And this has obviously some shortcomings. If you want a small object, then having maybe 6 sides is enough. However, if you don't know the size of your object, you have to prepare for the worst. And then if you want a large object with the same degree of resolution, angular resolution, you need to have many, many sides. And the approach depends, the complexity depends on the number of sides you are modeling. Of course, the more sides, the more expensive it is. So we can obtain large objects. In our approach, discrete optimization approach, we can obtain large objects without modeling it as a polygon with so many sides. So we have no problem, even if we have only 8 orientations, so we would have no problem getting a convex object like that. And we can also optimize it efficiently without using a GPU. So now let me talk about our discrete energy approach. So we are going to have an energy which has 2 parts. First part, well actually last part is the part which enforces convexity on your shape, and the first part will be your regular segmentation part that you would use for binary segmentation. It could encode the 2 terms we have seen before, that each pixel is assigned to the label it likes, either foreground or background, and regularity on the length of the boundary or anything else you might want to enforce. The important constraint we have is this part of the energy must be submodular, and that means you can optimize it exactly with a graph cut. And second part, we know, I'll show it's not submodular, so we're going to have to do something to deal with it in order to be able to optimize. So let's think about the constraints we need to enforce convexity on our solution. So what is convexity? You take 2 pixels in your object. So here we have a dark object, which is not convex in an image. I don't have actually a boundary for the image, but it's inside an image. So you have to, if you take 2 pixels inside your object and you take a line segment between them, then for any pixel on that line, that pixel also must be inside that object. Of course, here I have an example of a non-convex object, so we have a violation here. So what we need to do, we need to look at all triple pixels, at all triples of pixels like that that lie on a line segment, and we need to check whether they fail this constraint or they satisfy this constraint. That's exactly what we're going to do. So what is a violating configuration? Violating configuration, if you take 3 pixels like that, Q is in the middle and P and R on 2 sides. If we have configuration 101, we have a violation and we must penalize those. So therefore we're going to introduce a clique which depends on 3 pixels, so it's a triple clique energy. And whenever we have 3 variables in configuration 101, we're going to have infinite penalty. And if you wanted to write it out algebraically, what you're actually going to use for implementation, so xp is variable assigned to pixel p, xq variable assigned to the middle pixel, and xr is the variable assigned to the pixel on the right. That will be the functional form of the triple clique. Okay, so that seems, the beginning seems to be simple enough. It's really, really straightforward. So also what we need to do, we need to look at all lines under all different orientations, and of course we need to discretize the orientations that we have. So we're going to look at all lines under this configuration and look at all triple cliques on these lines. I'm showing you one triple clique, but of course there's a lot of them. So we're going to take another orientation, another orientation, another orientation, and as many orientations as we think is enough. And we're going to look at all triple cliques on all these lines and penalize whenever there is a violation of convexity. So therefore, our convexity term, the shape which penalizes, which enforces shape convexity prior, is the sum over lines under all different orientations. So if you saw this animation, that means we're summing under all different orientations. And for each orientation, we're going over triple cliques on all the lines under that orientation, and we put our triple clique, which enforces convexity there. Okay, so you just add up all triple clique values under all orientations. So there is a related work to that on how to deal with squared curvature. They have, in this previous work, they have an easier job, though they don't actually have to add up over all triple cliques on the line. It's enough to look at triple cliques locally. So they also model curvature by looking at triple cliques. They actually look at both convexity and concavity on the small line segments, but it's done locally, so it's much cheaper. In that work, there is order of n triple cliques you have to look at, and in our approach, the difficulty is if you count how many configurations, how many triples we have to look at. We have to look on the order of n squared triple cliques, which right away will tell you whatever you do, this problem is not going to be easy computationally. Yes.
The second approach, if the shape has a hole in the middle.
You mean for curvature?
Yeah, the curvature approach. If you have a hole in the middle, you don't see it.
Well, it depends on the size of the hole. It depends on how finely you discretize it. If you discretize finely enough, you will see it. But of course, yes, there will be approximation error. We could not do curvature here exactly, but it will be accurate up to discretization. So let's see. It's not just the number of triple cliques which is a problem for us, but our triple cliques are also not submodular, so you're going to have to deal with that somehow. And there's a very easy, nice graphical proof that convexity is not submodular, going back to the first principles of convexity. So the original the first principles of submodularity. The original definition of submodularity was on set functions, and here we can use a sets to visually see convexity is not submodular. So according to the definition of submodularity, if you have an energy function defined on sets, then energy on the union of two sets, S and T, plus energy on the intersection of two sets, S and T, must be less than or equal than energy on the two sets separately. So here visually you can see convexity doesn't satisfy this definition. Let's take two circular sets S and T. They're both convex. So as long as they're convex, there is no violation of convexity. So the energy, the sum will be 0. And for the intersection of two convex objects is convex. So again, no problem. Energy is 0. However, for the union is not convex. So the penalty, this object is not convex, so it will have infinite penalty, and therefore it's not, convexity is not convex. I hope I got it the right way, not the right way around. Okay. And it's not only that our cliques are not submodular, also naive evaluation would be very, very expensive. So we propose to address this problem in the trust region framework, which we have been advocating for optimization of difficult non-submodular problems in computer vision. So what is this trust region approach about? So suppose you have an energy function which is not submodular. Let's break it into two parts, the submodular part and supermodular part. What we're going to do, we're going to start with some current solution, let's call it xt. And at that current solution, we're going to construct a submodular approximation to our function, which coincides exactly at the current solution xt with the original function. So this is our submodular approximation. And I'm showing it as a convex function because convexity in continuous setting is a sort of a similar concept to submodularity. Of course, I also should point out this is a schematic picture of what's going on because we don't have continuous functions, right? So when I have my x is x, here x is not a real value. In fact, x is a discrete vector, but still sort of conceptually the picture shows very well what we are doing. how are we constructing the submodular approximation? What we're going to do, we're going to leave submodular part unchanged because submodular part is easy to handle. And for the supermodular part, we're going to replace with linear approximation using just the unary terms. So sum of submodular and linear approximation is going to give us submodular function, which is easy to optimize with a graph cut. So we're going to have, so again, at each step, we're going to construct submodular approximation, which coincides exactly with the current solution, and we're going to optimize it. However, we're not going to optimize it exactly. If we optimize it exactly, we might go so far from our current solution that the approximation doesn't really make much. Approximation is really far from the actual function. So if you take this solution, the actual energy, because we went so far from current approximation, our approximation we know is good only in the region around the current solution. If you go too far away, it might be really wrong. So if we take unbounded step, our next guess at the solution might actually have higher energy than what we started with. So what we want to make sure, we never go too far, or so far that energy goes up. So you're going to use trust region framework, which recommends optimizing your approximation not in the whole domain, but only in the region of trust, region around the current solution. So in this green region, we're going to try to find solution which doesn't go too far from the current solution. And of course, the width of this trust region will be changed as the algorithm proceeds. Maybe sometimes you can trust your solution, your approximation more than in other times. So the size of this trust region is not fixed. It changes according to how good you estimate your approximation function is. So that's what trust region framework, which is very well known and used in continuous optimization, that's what it recommends doing. Optimize this function in a band around current solution, in the band of width dt. Unfortunately, this is constraint submodular optimization. It actually is again NP-hard. If you wanted to solve it exactly, it's an NP-hard problem. So what we do, we replace, instead of having this term which says you must be exactly inside this trust region, we replace it by a term which is easy to handle and which is the same in the spirit. We don't actually, when we don't want to go too far from the current solution, we don't actually have to say that we strictly want to stay inside that region. Oh, that was my illustration for the trust region size. So what we can do, we can replace this exact constraint by something which is very similar in the spirit. We're going to introduce a new term in our energy function which will penalize deviations which are too far from the current solution. So xt is current solution. So we're going to measure how far is proposed solution x from the current solution, and that will not let us go too far from the current solution. The degree to which we penalize deviation from the current solution is controlled by lambda, and this is related to the trust region size. The larger is the lambda, the more penalty we put on deviation from the current solution. The smaller is the lambda, the more we allow our solution to get away from the current solution. And this term happens to be very easy, depending on the distance, of course, but say Hamming distance or Euclidean distance are very easy to put into the optimization framework using unary terms. So this becomes, this is modeled with the unary terms, and the whole energy is still submodular and easy to handle. So the strength of this lambda, the value of the lambda is controlled at each iteration. We can see how close our approximated energy to the actual energy, and if it's close, then we can decrease lambda. If approximation is not so good, then we increase lambda. Okay, so that's how we are going to deal with energy which is not submodular. So we're going to use trust region framework. Our energy has two parts, submodular part and convex part, which is not submodular, so we're going to construct linear approximation for it. So first thing we tried to do was very, very straightforward. First issue, we thought about, okay, we have n squared triple cliques. It's really, really expensive. So maybe it's enough to deal with just local convexity. Maybe you don't need to enforce convexity globally. Let's just look at the triple cliques locally, okay? So we're going to look only in some, for each pixel, we're going to look only in some region around it, not at the whole picture. And then we thought, okay, well, a second thing second question is, how do you approximate this convexity triple cliques? There are actually many, many choices we could make. And we thought, well, let's approximate only what we absolutely must approximate, and things which we can keep without approximating, let's leave them. What do I mean by that? If you take this triple clique, you can actually use very well-known decompositions and decompose this triple clique further. You can decompose it into a sum of submodular cliques and one supermodular clique. So you can isolate the supermodularity in one clique, and then there will be a bunch of other terms. So we thought, oh, that's great. We only have to approximate this supermodular clique, okay? And the rest of the stuff, this stuff, we can put into our submodular energy. We will keep it exact. We thought it's a good idea, okay? So only linearly approximate what's absolutely necessary in our energy, and the rest of these terms, move them into the submodular part. I probably even have, I have some errors later. Well, this approach had severe problems to the extent that it didn't work at all, and there are several reasons. First reason is easy to see and very understandable. This local convexity is very sensitive to noise. Now imagine we have our object, and nearby we have a small object, maybe even like 1 pixel object, but it's far enough so that our local convexity, the size of our cliques is smaller than the gap between these two objects. So if we use only convexity locally, we will not understand that this is a noise. We will think it's a valid convex object. So that was actually a minor issue, which you could deal somehow with post-processing. The worst issue is that it turns out, if you take this convexity clique, if you throw everything in it which is submodular in our submodular energy and approximate only supermodular part, it turns out you get a unary approximation which makes no sense whatsoever. So suppose this is current solution that we have. So we have an object which is not convex. So when we do unary approximation, we would like to get unary terms which are intuitive and interpretable. You can understand what's going on. However, and this is actually I'm decomposing here triple clique. What I'm showing here is this is the supermodular clique, which is hard to approximate, and this is actually decomposed into submodular parts which can be optimized exactly, so they can be part of the submodular part of the energy, but this is what we're approximating separately from that other term. So it turns out if you approximate only part of this triple clique, you get unary terms which don't make sense. Let me actually first show you the unary terms we want to get, and they would make sense. If this is current solution, you want unary terms which tells you for pixels here which violate convexity, put them in the background, and for this part which also violates convexity, put them in the foreground. So if you got unary terms like that, it would make sense. Let me actually remind you what the colors mean. Blue means this part wants to be foreground, blue wants to be foreground, red wants to be background. So these terms would make sense. They would move us from unconvex object to a convex object, put those in the background, put this in foreground. But we actually got terms, unary terms, separating this part separately from the rest, which absolutely didn't make any sense at all. Our unary terms actually said, put this in the background, put this into foreground, which is not at all what we want to do. If we do this flip, we're going to get, again, a non-convex object. So it turns out that if you have a term responsible for enforcing something, breaking it up into submodular, supermodular part like that, and approximating only part of this term doesn't actually give you anything which makes sense. So in our second approach, we are doing something differently. We said, okay, even though this triple clique, we could decompose and take submodular part, put it into the submodular part of the energy, and approximate only the small supermodular part of it, which we cannot optimize exactly. We're not going to do that. We're actually going to approximate the whole triple clique with linear approximation. We're not going to break it into parts. We're going to keep it as one entity, and we're going to approximate linearly this whole entity together. So we're going to use a unary approximation. So this triple clique is going to be approximated as sum of 3 unary terms, where coefficients A, B, and C are constants. And I'm not going to go into details on how we do this exactly, but it would depend on the current solution. Because remember, we're constructing an approximation which must coincide with current solution. So depending on the current solution, these constants A, B, and C change. And we still have the other issue that the number of triple cliques is very, very large, order of n squared. So we have to deal with it somehow. But it turns out for this particular unary approximation, it's actually fairly easy to come up with dynamic programming algorithm that speeds up computation from order of n squared to order of n. So that was also good. And we have to speed up both the evaluation of convexity and approximation. We always have to be able to estimate at each step the true energy E convexity, which also has order of n squared terms. Why do we have to know the true energy? Because at each iteration of trust region, we're comparing our approximation to the actual energy, and if approximation is good, we can increase the trust region size. If approximation is bad, we decrease it. So even evaluating E convexity is expensive, order of n squared, so we still have to do dynamic programming. And of course, for approximation, it's also order of n squared expensive, so we have to do it fast. So I'm only going to talk about how we evaluate efficiently the term E convexity. The other term is also a little bit more complicated, but also doable. So let's talk about evaluating E convexity fast. It's actually quite straightforward with dynamic programming. I'm going to show how to do it fast for one line, but then of course you do this over all lines. So we have one line. Say this line has n pixels, and the number of triple cliques there is order of n squared or even more. I can't think on the fly. I should have thought about it before the talk, but it's either quadratic or cubic. So let's take this line and let's look at current solution. And I like this animation very much, so I'm going to do it again. Okay, that's our current solution. Always works. Whenever I teach a class, I have a cool animation. If students are sleeping, this repeating animation twice always wakes people up. Okay, for those of you who are still sleeping, I can do it again. So how are we going to evaluate? So we have to evaluate how many triple clique violations of convexity we have. So here, black means the object, white means the background. So let's see. So this is the current solution on that line. One means object, 0 means background. So let's look at this white pixel here, the background pixel here, and how many violations of convexity is it involved. So it's involved in, for example, this violation, this pixel, that pixel, that pixel, or another triple clique, this pixel, that pixel, and that pixel. How do we know how many? Well, we have to see how many ones there are to the left of it and how many ones there are to the right of it. So for each choice of one on the left, there are many choices of the one on the right. So by doing simple counting, so for each of the two things here, there's 5 things there. So overall, it's involved in 10 violations of convexity. So this is for one pixel here, which is white, and the same goes for all white pixels. You have to know how many pixels to the left you have which are black, and how many pixels to the right you have which are black, and multiply. And this is actually very easy to count in linear time through one pass, using one pass through the line. So we can just go from the right to left and count how many pixels. For each pixel, we can count how many on the left are black, and the same in the other direction. And now it's one pass, so now for each white pixel, we just have to multiply these two numbers together. So we have 10 violations of convexity here, 12 violations of convexity here. So it's in two passes over line. We added up either quadratic or cubic number of terms. I forget. And so the total number of violations, and you add them up. Well, one more pass through the line to add up all those numbers for white pixels. So we have to do it over all orientations, and once we do it over all orientations, we will have computed our e-convexity exactly. Okay, so I remember how I showed you for if you decompose the clique and approximate only part of it, you get linear terms that don't make sense. If we actually now approximate the whole clique, we get unary terms which make a lot of sense, and in fact this approach works quite well. So let's look at the illustrations here. So here we're trying to separate black object from light background, and of course with noise. So here is the input to the algorithm. So here we have object, convex object with noise. We have object with sharp angles with noise. We have two separate objects, object with holes, or sort of like this wavy crazy thing. And here are the final solutions our algorithm obtains, which are quite reasonable. To the red is the outline, or you can see the mask, solution mask. What's interesting is to look at the unary terms we get from convexity approximation. They make a lot of sense, these unary terms. So, for example, here, what we get unary terms in this region, or in the region of the circle, they say switch to the background. Also, for example, let's look here. The unary terms in the regions where there are holes also say switch to the foreground. If you look at this example here, you want to fill in the region between the two separate dark blobs, and the unary terms again say fill that region, and so on. So looking at these unary terms, you sort of see where our approximation drives the solution to, and at second iterations, these unary terms become sharper. So these unary terms encourage filling of holes and removal of protrusions. Of course, we're not guaranteed to get, before I get there, we're not guaranteed global minimum. It's an iterative approach. It can get stuck, and I'll talk about that. So let's look at some results on real images. Suppose we have a hedgehog image, and user marks some scribbles on it for foreground, background. We use these scribbles to model appearance of the foreground and background terms. So let's see, if you use no regularization at all, if you just threshold this image based on the appearance you get from scribbles, then you get a very noisy result. Now let's look at the results we get by changing the regularizer weight. And first let's look at the length as regularizer for this example. So I'm not using convexity here, I'm just using regular strength. I'm using strength for regularization. So here we chart distance from ground truth. So we know, of course, ground truth in this case, we extracted it manually. So let's look at how the solutions change, and let's plot regularizer weight versus distance from ground truth. And you can see for the length, there are several, 3, or depending on how you look, 3 or 4 breakpoints where the solution changes sharply. So let's look at point A. At point A, we basically have no regularization yet. That's what length gives us, very noisy solution. Next, we have roughly in this region of weight, solution B. Solution B is more regular, but still doesn't give us a good separation between foreground, background that we want. And at this level, we have, once we reach this value, we get solution C, and it more or less stays the same throughout. Here we have user scribbles back, so we don't get for any value of regularizer good solution. Let's now compare it with convexity. Let's look at the same thing, where we increase the strength of convexity. By the way, I think I forgot to mention, I said that we have a penalty, infinite penalty for triple clique which violates convexity in practice. Of course, we still have to put some finite weight W there. We cannot use infinity. So there, and we have to choose this W somehow in practice. So let's see how W has to be big, but let's still see for smaller and larger value of convexity penalizer at what solutions we get. So this is the curve we get for different convexity weight W. Notice how close we are to ground truth, and there's actually very little variation in the solution that we're getting. So let's look at different points in the very beginning at regularizer weight 0.1 until larger weight of 10. We get, it's not an identical solution, but we get solutions which are very, yes?
How much is it helping that your foreground scribble is non-convex?
That's a very good question. It doesn't really matter, but what really does matter is the initial solution we start with. In fact, if we start with initial solution which happens to be convex, very unlikely algorithm will not move anywhere. But it's not, the shape of the scribble doesn't matter at all. What matters is if you, so the scribbles are used to construct initial solution, and initial solution is based on just assigning each pixel to the label it likes most. So it's very unlikely it will be convex in the beginning if you just use data terms. But yes, if you start with initial, if your data term happens to give you convex solution, you will not move anywhere. So we'd like to say, looking at this graph, it's not quite completely true that our method is parameter free, but virtually parameter free, and I'll explain what I mean by virtually parameter free. Why is it not completely parameter free? Because of course, for this example, there's not much difference, but you can find examples where there's a little bit of a difference between starting with small w and large w.
What is the size of the term that is in front of omega? Is omega 0.01 already close to infinity?
So omega here is 10, and there's
but it's multiplied by the very large sum.
No, omega is the actual value we're using for, if you have any violation of convexity in our triple clique, that's the omega we put 10, but we have lots of them, right? And you also have to ask me what is the data term, on what scale is the data term that we're using, right? Because it's omega only relevant in relation to the data term, and the data term I wouldn't really remember on what scale, but I assume it's from like 0 to 10, 0 to 20. Honestly, I don't remember, but obviously if it was on a different scale, I could redo this plot. Some other results, of course, there are many cases where length regularization does just fine. So in this particular example, with weight 2, with weight 8, you get good results, and with convexity, you get also good results. But since I'm talking about convexity and how convexity is a good shape prior, of course, we found plenty examples. This one I have shown you before, how like a small switch in the weight regularizer for length leads you to drastically different results, and there is no good middle, or at least you'd have to search for a very long time for a good middle between those two values, and some other results. Obviously, when we were constructing this example, I mean, there might be actually more of these examples in H, I don't know, but we were interested in examples where length regularization fails, and fails spectacularly in the sense that really between the two nearby values, there is no good, at least not easy to find a value where you get good results, and with convexity for more or less the whole range of values, you get a good result. Yes.
Shouldn't you be initializing your length regularization algorithm with the convex hull of the scribbles?
Since the algorithm, since in binary case you get global max, global minimum, it doesn't actually matter what you initialize with. You will get exactly the same solution.
If you know you're looking for a convex object and someone scribbles something, you should replace this scribble by the convex.
If you know you're looking for convex object, you should be using convexity shape prior that I'm talking about.
Yeah, but I mean, I think on this image, on this image, the convex hull of the scribble is very close to the solution.
Well, these are the easiest examples to generate for us using user scribbles, but then you can do things based on appearance, and I was showing you in the beginning some results some images where you don't have user scribbles. You do it based on the model of the color, right? Which you have, like black or white object. You're looking for dark object on a lighter background. So these were just the easiest in terms, from the point of view of the experiment. These were just the easiest for us to work with, but you don't always have user scribbles. Yes, okay. If you wanted to have a super fast convexity algorithm and you have user scribbles, one could imagine you can ask the user to outline your convex object, right? And that would be
I mean, just to word that differently, how does the solution change when I add a new scribble? So in the middle column, if I add a new scribble inside the convex area, that will definitely change the solution?
For when you're using length regularization,
yeah,
you will change, depends on how you use that scribble, because if you use it to model appearance, your appearance might change, and that can change the solution drastically. If you use it as a hard constraint, also likely to change without re-estimating the model. We will also do, depending on, if you scribble foreground here, obviously it's going to change solution somehow, but in a less predictable manner. So some results on medical images, user scribbles, input image user scribbles result with no regularization and result with convexity regularization. Running time is also for our regularizer. So it's quite reasonable. Maybe it's not in, for the larger image, it's not going to be under a second, but it's still quite a reasonable running time. So we wanted to compare some other optimizers, not just our own trust region framework. So we took some standard optimizers. We wanted to compare with, say, QPBO and TRWS. And Vladimir is always mad at me when I'm saying we're going to compare with QPBO plus TRWS, because he tells me it's exactly the same algorithm for binary case, and I tell him, well, we're using your code, and your code gives us different results. Because, okay, and I'll explain why the results are different using his code, because the way he extracts final solution is different. Still, this is the code out there available for nonsubmodular optimization, so we ran it, we did nothing criminal, even if Vladimir is upset. So in order to compare to previous methods, we're again facing this challenge that we have order of n squared triple cliques, and it's just too prohibitively expensive. So, but we wanted to try to do something reasonable, and we came up with a compact convexity model, which in practice probably is still quite expensive, but at least it's reasonable enough in terms of running time to try other optimization code. And in the compact model, which I'm going to explain in the next slide, we have not order of n squared, we have a smaller number of cliques, so we have n times square root of n number of cliques. It's slower. Interestingly enough, it has less cliques. However, for our approach, we cannot use dynamic programming anymore. We cannot have the same savings. So it's a weaker model with smaller number of cliques, but dynamic programming doesn't apply, so our method will be actually slower than the full model. But we use it just for comparison with other optimizers. What is this central clique model? Well, the name says it all. How about instead of using all triple cliques, we only use triple cliques which are centered where the distance between middle pixel to the left and to the right is exactly the same. So we're going to take pixel Q and we're going to look exactly D on the right, distance D on the right, distance D on the left, and we're going to look we're going to take all such triplets on a line. So it gives us significantly smaller number of triple cliques, but no dynamic programming anymore. So we can look at the results. Again, input images, user scribbles from which we get color appearance. And here's a comparison of using all cliques without dynamic programming. These are the results we get in 2.4 seconds, 4.6 seconds. Now using a smaller model, but no dynamic programming, so we actually get pretty much the same result, almost the same result, but running time, of course, is significantly larger because we have to compute things in a more straightforward manner. But still, this gives us a good baseline for comparison. Okay, so we tried QPBO and TRWS and our method, again, for different values of regularizer, strength of regularizer. Here we have some white object on a black background, and we want to try a convex approximation of it. Here results we get with omega equals 10, our energy value, running time 18 seconds. QPBO doesn't manage to label a single pixel. TRWS gives us something with a much, much worse energy, and pretty much the same picture for different values of omega. We always get much better energy, so you have to compare this number to that number. For small omega, actually, we get equivalent solution, but we don't get convex result because it's too small. Omega is too small to enforce convexity. Starting when omega is large enough to try to get something more convex, our energy is much better than TRWS, and QPBO doesn't label any single pixel, and this is true for every other value of omega. So our trust region approach is much better than previous approaches in terms of optimization. Of course, we are dealing here with a method which can get stuck in a local minimum. We're not guaranteed global minimum, and in fact, it is sensitive to initialization. So for example, here, let's take these two examples. If we start with initializing everything as foreground, we get non-optimal solutions like that. And if we initialize everything from the data term, so that shows the outline, so from the data term, what pixel references for the foreground, we get solutions which are global minimum. So there is sensitivity. It's more striking in the artificial examples like that we came up with. In practical examples we have tried, it's not such a huge difference between non-optimal and optimal. So I guess the difference is largest here. But we do see it on real images sometimes as well. So for example, here, if we take this particular problem and we run our approach with omega strength, say 100, we do see that this little bit corners of the shape cut off. We actually want to extract the whole organ, including this part. So what we found helps. So we found if we take large convexity strength, then we might have this local optimum problem more than if we don't. So we came up with a annealing approach which alleviates, so these are the missing parts that we would like to get. So we came up with an annealing approach which works as follows. You start with small regularization strength, small convexity strength, and say you get result like that. Then next iteration you initialize with small convexity length, and then you increase, you anneal the strength of regularization until the last value, and this way you can obtain better results. So again, this is just sort of a practical trick we found that works well. So summary for single object convexity is I've shown how to implement it within discrete optimization framework. There is no shrinking bias, removes noise, fills in holes, ensures connectivity, preserves sharp corners, and it's basically scales virtually parameter-free, which is not quite completely true, but if you do annealing is more expensive, of course, when it becomes much more true, and efficient optimization based on trust region dynamic programming. And sorry, I've only got through one part. Somehow I thought this was half an hour, but I'm not going to go through the other two parts. Okay. So, but they were very exciting.
I like the trust region approach, but it seems constructing a surrogate function is a bit of a black art. Are there any insights or recommendations?
Well, this is one recommendation that I have mentioned, which again was really striking to us, is that if you have some term for ensuring something, even if it seems like a good idea to decompose and take all the submodular parts out, what we found, quite our surprise, dealing with just part of it, got you derivatives that got you approximation that made no sense. So one way is to sit maybe and think about it. So all our approximations are based on Taylor expansion, which is not necessarily the best one, but it seems like the easiest thing to do. So like so what I would say, do not if you have a term for ensuring coherence of something, do not decompose it, deal with it as one object by approximating it as one object.
Encounter an example where the opposite was true. So we're decomposing it or rewriting it led to something better, or?
Not in my experience. It might exist, I'm not saying it doesn't, could well exist, but not in my experience. Also, what worked better, we also have some extension of this work, which instead of doing unary approximation based on Taylor expansion, does pairwise approximation. And that actually works very well without the kneading. You can get good results. Like whenever you have problems which we solve by kneading, if you do quadratic approximation, you get better results. The problem is for convexity, it's expensive if you do pairwise approximation, because you have order of n squared terms and it's too expensive.
Pairwise submodular.
Pairwise sub. So you do an approximation. Yes, you do. Yes, pairwise submodular, exactly. Well, I don't have much time. So you start with pairwise approximation. Some terms are not submodular, and those which are not submodular, you actually approximate as unary ones. So having high order approximations works better, but for convexity, it's not really feasible because you have too many cliques, and then programming there doesn't apply. But for other problems, so you don't have as many cliques, it might work. For curvature, we thought about applying it for curvature, but for curvature, actually, you only have pairwise cliques. It starts with triple cliques, but once you decompose, you actually only have pairwise non-submodular cliques, so their pairwise approximation would not make sense. Would not, I mean, doesn't apply.
Well, what if you have like a non-flat domain, like a surface? Can you generalize these ideas by appealing to the notion of geodesics or something?
A very good question. Yeah, I don't see why not, because we're measuring convexity on lines.
Convexity principle, would that hold?
Well, I mean, convex, you take a line in 3D space, right? Actually, yeah, I think it should be still okay. It's just much more expensive in 3D.
So you have several notions of convexity because you have several
Exactly. Yes.
geodesics connections to lines.
Can this easily be extended to 3D numerically?
So underlying problem we constantly have to solve is a graph cut. It's easily generalizable to 3D, but of course, I mean, in 3D you have to pay more. But yes, it would totally, like, there's no issue going there from 2D, except complexity, computational complexity. Yeah, but it completely goes into 3D. So if you can, like, I'm not aware of multiple notions of convexity in 3D, but as long as you can somehow formulate it on cliques, triple cliques, or you could go to high order cliques. Maybe you need to go to. So I assume that you going with high enough order of cliques, you can model any notion of convexity in 3D and higher. Just your approximation may not be, and you can always approximate things linearly, but of course these approximations may get worse and worse if you do linear approximations for high order objects.
It feels like, I don't know if this is true, but it feels like there might be a reasonably efficient algorithm to check if a bitmap is convex, contains convex set of ones. And then it feels like you might have an algorithm which is based on most violator constraint or any violator constraints. Did you look at that? Or
so you're asking why we count all violations instead of going for most violator something. We've actually, was that your question? So this work actually, when we started this work, this is the first thing we've done. We've tried to find violation of, there's actually like a very efficient algorithm using graph cuts, which was really cute, to check whether the object is convex or not at the start. We never published anyway, even though it was cute, but turned out to be useless in the end. And we started with taking violated constraints that we found and approximating those, but it actually really didn't work well. I forget the reason we found, because this work, and actually the project ended there. So this was like maybe 7 years ago, that's what we've tried, and we didn't know about trust, we didn't have trust region framework then, and the project stopped because that approach seemed to get stuck very easily. Oh yeah, I remember what happened. What happened if you use most violation constraints first, we would get stuck in a bad local minimum. We'd get convex object, which was horrible, but no violations, it wouldn't move anywhere. That's what happened. And then once trust region framework came to be, we sort of found it useful, then this work came out and we came back to our old failure, and this worked much better.
So you check all the direction. In practice, how many directions you use in your computation?
Good enough to have nice pictures. I don't actually remember. I think maybe it was 16 directions.
16 directions.
If you look at memoir, say 32 until you're happy. I don't know. Just as many directions as to have nice looking pictures. But obviously, if you want more resolution, then you have to take more directions, right? So I think 16.
Yeah. Does this correspond to 16 gons if you
No.
if you have the polygon?
Because we don't, yeah, they would have to do, I think our 16 would correspond to more sides, because when I say 16, sorry, I actually mean it in one quadrant, 16. So that would be, I don't know, multiplied by what?
Yeah, but this other, the Kramer approach with the polygons, if they take 16 gons, it would correspond exactly to your 16 directions.
Not quite, because there they also have, like if you have a smaller size object and larger size object, they physically, if you have, say, 16-sided polygon, they physically could not have a nice, if it's a big enough shape, because they have to have 16 sides, it cannot look like a nice circle. It's going to have 16 sides, where even if you're using 16 directions, we can still get a circle, because there's nothing which says our object has to be 16-sided polygon. We actually, due to the data term, depends on the data preference. We're not modeling, okay, another way of saying it, you might say it's sort of cheating if you're unkind. If you're kind to us, you will think it's great. But we are looking at violations of convexity at certain angular resolution, but we're not preventing an object to be of any shape we want. If a data term wants it, it will be of any shape. Whereas they actually physically preventing it from being of any shape by saying it must be a 16-sided polygon or whatever, how many sides. They just forbid the circle, where we don't. We just don't look as finely as we could. But if the data says I want a circle there, you'll get a circle. Okay, so.
Okay, we thank the speaker once more. For some of you, if you are here first time.